most common way to determine the acidity or basicity of a solution is to determine the pH. So pH is looking at a negative log of the hydronium or H plus concentration. So we use hydronium and H plus interchangeably, so you can also do the negative log of the H plus, okay? So same thing. So now one thing that we don't write, okay, is that it's log base 10 of the H plus, okay? Because we work in a base 10 system. So, and it's negative log here. So what this means is that because it's a negative log, the lower the number, the stronger the acid is, okay? So the smaller the number, the more acidic it is. When I go from something like a pH 6 to a pH 5, pH 5, because it's log base 10, is 10 times more acidic than the pH of 6 is. pH 4 would be 100 times more acidic than pH 6. pH 3 would be 1,000 times more acidic than a pH of 6 would be. Okay? And I have this notation here with this bracket. So anytime we use these brackets, anytime you see any species inside these brackets, we're dealing with concentration in molarity. So I put those brackets around anything, not just the hydronium ion. Anytime we use those brackets for anything, we're talking about molarity. Okay? So we're looking at this negative logarithmic scale. If you're familiar with earthquakes, we use the Richter scale. That's a positive logarithmic scale. And so same sort of a deal, except now the stronger the earthquake is a higher number because it's a positive scale. And so if I have like a magnitude 4 earthquake versus a magnitude 5, that magnitude 5 is 10 times stronger. A magnitude 6 would be 100 times stronger. A magnitude 7 would be 1,000 times stronger. Okay, so you want to keep that in your mind when you think about as we change these. Okay. To measure the pH, we can use indicators. These are things that are colorful. They're not going to give us a super precise reading on the pH, but they'll give us an approximate pH. To get a more accurate reading, we use a pH meter. Okay? That gives us an actual numerical value there. So again, pH of 7 is neutral, more than 7 is basic, less than 7 is acidic. Okay? I like this picture over here. So there's tons of different types of indicators. Some indicators only indicate over a small pH range. Other ones we can get over the entire pH range. This indicator is cool because it's made from red cabbage juice. So you can buy a red cabbage from the grocery store, boil it, get this purpley juice here, and add it to different things, and it'll change colors based on how acidic or basic it is. Okay? We can get a related term, which is the POH. So that's just the negative log of the hydroxide concentration. We don't do a whole lot with POH, but we're going to use it a little bit in the context of what we're studying right now. It's used sometimes, but because we think of the acidity of something based on the above or below 7 value, most of the time we just deal with the pH. So here's some pH values. Take a moment and see if you can decide based on these numbers if these solutions are acidic, basic, or neutral. All right, let's see how you did. Well, the egg white at pH of 7.9. It's not terribly over 7, but it is over 7, so it's basic. The maple syrup, that's neutral because it's exactly 7. And then all the rest of these are below 7. So those are all acidic. Okay? Now let's try doing some calculations. So here's the thing. This is really, really important that you do these alongside with me. All right? When you take your test, you have to use your calculator. And one of the biggest struggles with these pH calculations is using your calculator, because not every calculator has the same keying sequence. So you need to practice with your calculator to make sure that you can replicate the answers that I'm getting as I explain these problems to you. All right, So first off, let's do the pH of this 0.1 molar solution of hydrochloric acid. Okay, hydrochloric acid is a monoprotic acid. So when we talk about this, when hydrochloric acid disassociates, it disassociates into that H plus ion plus a chloride ion. The H plus ion we call a proton. Because if you think about H plus, okay, if I have a hydrogen atom, I've got one proton and one electron. If I lose that electron, now all I have left is a proton. So an H plus atom we call a proton. When I say monoprotic, it means I have one proton that can come off when it ionizes, okay? And again, H3O plus, H plus, they're used interchangeably. Okay, so we've got this hydrochloric acid solution, hydronium ion concentration of 0.1 molar. So to get the pH, we're going to do the negative log of 0.1 molar. Okay. All right, so when we take the pH, we're going to get 1.00. Now, let's talk the significant figures of logs. They're kind of weird. I could rewrite 0.1 molar as 1.0 times 10 to the negative first. Okay? So here I have two significant figures. Okay? And my 10 to the negative first I have is my exponential. When I take the log, the number that comes before the decimal point, this is related to the exponential. Okay? And the numbers after the decimal point, those are your sig figs. Okay? So I've got a number related to my exponential, and then I have my sig figs. Okay? Let's try a couple more. So I've got some table wine. I let it age. So let's calculate the pH before and after I let it age. Okay, so there's before it ages. We get 3.49. Again, the 0.49, those are the two sig figs, and that 3 is related to the exponential. Okay, and then after it aged, we get negative log of 1.0 times 10 to the negative third, which gives us 3.00. Okay? All right. So here are 3 for you to try on your own. So again, really important that you practice these and try these with your calculator. When I teach in-person classes especially, like I get so many questions on, I don't know how to put this into my calculator. So definitely got to work with your calculator. If you're struggling with your calculator, pop into office hour. If you can't make my office hour, email me, schedule a meeting with me, camera on so we can look at your calculator and we can try and figure out where you're struggling with your particular calculator. The TI, what is it? The TI-30XS. I think that's the one, the single line entry one. That's the one I think students have the most number of problems with. Okay, so try these. Pause the video for a second. All right, let's see how you did. So your first one, the carrot juice, you should get a pH of 5.10. Your pea juice, you should get 6.41. And your pure water, you should get 7.00. Okay, again, all of these have two sig figs, and so we have two numbers after that decimal once we take the pH, because that's related to our sig figs. Now, we have this pH loop, okay? I have a whole bunch of interrelated terms here. Whenever I'm dealing with pH, I'm also dealing with hydronium ion concentrations, hydroxide ion concentrations, and this POH. So we looked before at this right here. Okay, this is that KW number. Okay. Now, we just did an example where we saw that the pH of pure water was 7. In pure water, we know that the hydronium and the hydroxide ion concentrations are exactly the same. So our pOH of pure water would also be 7. Well, what's 7 plus 7? 14. So we have this relationship right here, where the pH plus the pOH is equal to 14. All right, and then again, remember we're dealing with this log base 10, and so to reverse the log, we do this right here, the 10 to the negative pH. Same thing with pOH, it's a log base 10. So to reverse the log, we do 10 to the negative pOH. Okay, so I can start anywhere. If I know the pH, I can calculate the pOH, I can calculate the hydroxide, I can calculate the hydronium. If I start with the pH, I could go the other direction. I could calculate the hydronium, the hydroxide, and then the pOH. I could start with hydroxide. Same thing. I can go around the loop, either direction. And so as long as I know one of these 4 values, and I know this relationship here, I can calculate any one of the other values. Okay? All right, so let's first just practice a few calculations. So to start off with, I want to know the pOH of a solution that is 4.87 times 10 to the negative 9th molar sodium hydroxide. Well, to do that, we need the hydroxide concentration. So here's the thing. We need to look at the formula. Sodium hydroxide is nice because there's one hydroxide there. This is an easy one. Okay, so if I have 4.87 times 10 to the negative 9th molar sodium hydroxide, and I have one hydroxide ion for every one sodium hydroxide, this one's really easy in that I also get 4.87 times 10 to the negative 9th. Okay, now if this were something like barium hydroxide, where the formula is Ba parenthesis OH with a 2, there's 2 hydroxides. So this stoichiometry would give us twice the concentration of hydroxide. So you have to pay attention to your formula when you're figuring out what your hydroxide or hydronium ion concentrations are. All right, so now my pOH is just the negative log of that hydroxide concentration. So it's 4.87 times 10 to the negative 9th. Okay. All right, we have 3 sig figs this time. So you get 8.310. Okay. All right, now let's try reversing a log. So we already have the log taken. So this pH 4.22. So remember, once the log is taken, we have 2 sig figs. Okay, because we're already in the pH. So to reverse that, to get this hydronium ion concentration, we're going to get 10 to that negative pH, so 10 to the negative 4.22. Okay, so this is going to give us 6.0 times 10 to the negative 5th. Okay, and again, these brackets, that's concentration and molarity, so that's molar. Okay, all right. Now, let's try one where we have to do a couple of calculations. So I have a sodium hydroxide solution. I have a hydroxide ion concentration of 0.1 molar. What I want is the pH. So there's 2 ways I can do this. Okay, method 1, I can do hydronium is equal to the Kw over hydroxide. Okay. And then step 2 would be the pH is the negative log of that hydronium. All right, or method 2, I can go in a different direction because remember that loop, there are 2 ways we could take. So method 2, I can do the pOH is equal to the negative log of the hydroxide. And then remember, pH plus pOH equals 14. So if I know the pOH, I can do 14 minus pOH to get the pH. So pH here would be 14 minus pOH. Both of these work, okay? I'm going to do method 2 because we've calculated KW once before. So I'm going to do method 2 just so that we can practice this method right here. Okay, so POH, we're going to get negative log 1.1 molar. So we're going to get 1.00. And then we'll get 14 minus 1.00 is going to give us 13. Okay? All right. Okay, so here's another one. We have sodium hydroxide again. Okay, so building on the similar example, we want to know the pH of this sodium hydroxide solution. So again, 2 methods you could take. All right, I'm not going to solve this whole one for you. I'll give you the answer. Okay, let's see how you did. You should get a pH that is equal to 12.38. Okay? All right, now I have a big old chart. Again, once you know one value, you can figure out any of the other values. All right? So, again, I want you to practice this. If you didn't download the slides and you're just watching the video, you can't see the last number I have in the corner here. So this POH value down here is 12.91. Okay? Now, if you look at this chart, what I have going on here is I have 3 sig figs here. I have 3 sig figs here. This is the pH, it's already been taken, so 3 sig figs. But down here, my 12.91, okay, the 0.91, that's 2 sig figs. All right, so I want you to try this and make sure you can get the sig figs on this too. So again, try this, okay? Pause the video, try calculating these, and then unpause, and I will give you the answers. Okay, let's see how you did. So let me fill this in. This should be 1.58 times 10 to the negative 9th molar. Now, if you went around the pH loop differently than I did, sometimes when you round off at different stages, maybe you would get 1.59, maybe you got 1.57. That's perfectly fine, all right? Because it still is the same answer. That very last digit, so if you're off by 1, that's just a matter of rounding how you go around, especially if you use the KW division. Sometimes if you round that off before moving on to the next step, you end up with just a tiny little difference. Okay? All right, pH is 5.199, POH 8.800. Okay? This one we get 2.48 times 10 to the negative 9th molar. A pH of 8.605, a pH of 5.395. Okay, 1.28 times 10 to the negative 11th molar, 7.82 times 10 to the negative 4th molar, and then 3.107. Try to squeeze that in there. All right, and our last one, we're down to 2 sig figs. So I have 8.1 times 10 to the negative 2nd molar, 1.2 times 10 to the negative 13th molar, and 1.09. All right, so those are our pH calculations. So if you struggled with any of this or you're having problems with your calculator, please reach out. Let me help you figure this out before you get to a test environment and you can't ask how to use your calculator. All right, so if you struggle with these, reach out. If you didn't, if you were able to get this, excellent. And now you understand pH.